Hello everyone, welcome to the Business Intelligence course. Understanding how to leverage and use the data and information assets residing in your organization to create tangible benefits is the basic focus of this course. Professionals with a strong quantitative background in business analytics who have a focus on business intelligence and customer analytics are highly desired in this course. This course has been designed to support the participants to develop domain-specific competencies to leverage dynamic aspects of business processes. We will be specifically talking about selection and prioritization systems or advanced decision support systems in this course. Selection and prioritization systems specifically facilitate selection among alternatives in a multi-criteria decision-making problem. What this means is that there will be a problem and you have to make a decision out of all of the different criterias which are being shown to you. For example, let us take an example that there are some n number of mobiles and you want to choose the best mobile for yourself. Now, every mobile has some feature associated with it, be it price or camera specifications or storage size. You do not know which mobile you want to buy for yourself. For example, you might only consider the price as a very important feature when thinking about choosing the best mobile. You may not decide about the storage or the camera specifications while doing so. This selection and prioritization systems, or SPDSS, compares all of these features of every mobile like they're apples and oranges and makes the decisions objectively. It facilitates this group decision making in consensus, and it enhances the goal analysis and prioritization of your goal. The decision support systems for selection and prioritization can be solved with different approaches. We will be specifically talking about two approaches in this presentation. The first one is Topsis, and the second is the analytic hierarchy process. We will be talking about AHP or analytic hierarchy process first, and then we will be moving on to Topsis. Let's talk about analytical hierarchy process. AHP or analytic hierarchy process is a method for mathematical treatment of decision problems. As explained before, a decision problem is some problem in which you have a lot of data, maybe in the form of different features, and you want to make a particular decision by choosing some data item. This decision problem can take many forms. This is one particular example of a mobile that I was giving you. AHP is based on Eigenvalue problem. As I've explained before, in AHP, values like price, weight, or area, and even subjective opinions such as feelings, preferences, and satisfaction can be translated into measurable numeric relations. Why is this done? This is done so that there can be some form of weighting or ratio analysis between each of these values. If these values were not transformed into numerical values, then it would have been extremely impossible to do some kind of analysis between these values. Any kind of correlation or ratio analysis between the different features, for example, in the case of a mobile phone, needs to be done only when these values are converted into numerical values. The core of AHP lies in deriving ratio scales, as I just talked before, from paired comparison instead of sorting or voting. AHP can be applied to many business problems in several cases. Example, identification of witness in a criminal case, decision for buying an MP3 player or mobile, and the survey-based analysis of political candidates. Now, we have discussed about what is AHP. Now let's talk about what is the work which has been done in AHP. An analytical hierarchy process has been under major research over the past couple of years. Over 2,000 research studies have used AHP for different multi-criteria decision-making problems over numerous domains. As you can see, a multi-criteria decision-making process is also called MCDM. And as you can see in figure 1, these are all of the review papers pertaining to AHP in a theme-specific distribution. And the different themes can be selection, evaluation, benefit cost, priority, development, resource allocation, and forecasting medicine. So AHP has all of these applications when we are looking at the themes. And every theme, for example, every theme can be pertained to a particular area. For example, if I'm talking about manufacturing, there are approximately 18% of the review papers, which are 2,000 review papers, 18% are related to manufacturing in AHP. So application of AHP in manufacturing can have all of these themes: selection in manufacturing, evaluation in manufacturing, benefit cost, priority, development in manufacturing. All of these things can be done for a particular application. So there is extensive amount of research and work which has been done in AHP over the past couple of years. So this makes it a very important decision-making algorithm or approach. When do we know that we need to use AHP? The first thing is the problem should have multiple criteria or features. That is for sure, because AHP is an MCDM approach. And then when there are non-comparable criteria for evaluation, all of these features cannot be compared. For example, if I'm talking about a mobile phone, the price and the storage space cannot be compared. So that is an important criteria for evaluation. And when the decision point can be broken down hierarchically, this is extremely important. Now, let me give you an example. For example, yes, you can look at this AHP problem, this supplier evaluation. For example, we want to know the evaluation of a supplier. We want to evaluate a supplier. Supplier can be any person who is supplying any information or any material to other persons. So we want to evaluate him or her. So we break it down into 4 parts. He can supply logistics, he can supply technology, he can be a business supplier, or he can be a normal relationship supplier. If he is supplying logistics, then these are the different characteristics or features which will be pertaining to logistics supplier. Similarly, technological supplier will be pertaining to these different features, and so on and so forth. So this breakdown is very important. This hierarchical breakdown is very important when we want to solve the problem using AHP. We can look at another example. If there is a goal that we want to solve, and for that goal to be solved, we look at 4 different features. Let's say damages, applicability, added value, and cost. If you look at, for example, damages, so there can be different types of damages: product damage, people damage, image damage, flamed, I think this is plant damage. Plant damage can be direct and indirect both. Environmental damage can be external or internal. Production loss can be, I'm not able to understand these two, but you get the idea. So all of this is hierarchy. So that is why it is called AHP, analytic hierarchy process. Now let's move back. When the decision making can be done taking 2 dimensions at a time. This is very important because we will be constructing a matrix in which we will be assigning weights which for example, if we have a matrix and the cell I comma j will be storing some particular value in terms of some fraction. If that value is, let's say, 0.3, this means that where the feature number I will be 0.3 times more important than feature number j. So we will be comparing the features by taking these dimensions two at a time. When the problem is linguistically simplified and less quantifiable, so you can understand the problem easily and you can break it down. Yes. And when to use AHP? When group decision making is required. So yes, when the decision making requires the complete group, you have a lot of features and you want to use all of them to make the decision. Okay, so now let's discuss why should we use AHP. There are many reasons why a person should use AHP to solve the particular decision making problem. One of the most important reasons is that it provides a systematic approach to improve the consistencies of all of the priorities of the features. So you have a lot of features and you assign them different priorities. The main question is that you do not know initially what priorities do we need to assign to each feature. For example, in the case of choosing the best mobile, you don't know what is the priority to be assigned to what are the weights which we need to assign to each of the features. For example, storage or price. So AHP helps us in this. It also provides different methods for aggregation of the group preferences. So these are some reasons why we should use AHP. And moreover, it has extensive theories to estimate consistency of priorities of the decision makers. Now, let us look at a brief overview of how AHP works. You have the actual measurements or the subjective opinion in the form of price, weights, satisfaction, feelings, preference, etc. These are the inputs to the AHP approach, AHP model. And the output is a consistency index and the ratio scales. The ratio scales provide us with the different weights which are to be assigned to each feature. So these are the ratios, and these are derived from eigenvectors and eigenvalues. We'll be looking at an example to see how the whole AHP process works. The analytics hierarchy process is defined like this. You define the objective, what you want to solve. Then you define the structure elements and criteria and sub-criteria alternatives. This is done in a hierarchy, as we have just seen. This is the goal. These are the decision attributes which we want to, which are directly related to the goal. And then we basically look into further more detailed decision attributes. Then you make a pairwise comparison of elements in each group. After doing this, we calculate weighting and consistency, and then we evaluate alternatives according to weights. In the final step, we get the ranking. So now let's look at this example we have already discussed earlier. So now let's look at the different methods which are used to solve AHP. So there are different methods which are used to solve AHP. One method is eigenvector method, then weighted least squares method, additive normalization method. Then there are many other methods which are basically used to solve AHP problem. Let's look at an example to understand the AHP process more elaborately. We have different vehicles, for example, Maruti Ignis, Hyundai i10, Maruti Swift, etc. And for each vehicle, we have a vehicle type, hatchback, sedan, or SUV, color, and the mileage that it is providing. We want to choose the best vehicle for us. Now, we don't know because for some people, color might not be very important, but mileage, for most of the people, mileage is very important. That is for sure. Then for other people, color might not be important, but vehicle type might be very important. So we don't know what kind of weightage should be given. So now this is the weighted scale which you will be using. For example, if I'm talking about color and vehicle type, so color, for some people, if you are the person for whom this problem is being solved, you might give a weight of 1 to both color and vehicle type when drawing the matrix. So now let's look at the matrix. There are going to be matrices of this form. The first matrix will be for each feature like vehicle type, color and mileage. So vehicle type, color and mileage. And these are the weights that we give. For example, I just discussed vehicle type, and vehicle type is 1, color and color are equal, mileage and mileage is given as equal. Now vehicle type and car color is 0.5. This means that vehicle type is, for example, the price of vehicle type will be, let's say if the price of vehicle type is X, then the price of car color will be X by 2. This means that car color will be half of what important vehicle type is. So vehicle type will be basically more important than color, twice as much. Okay. So if the car color is X, vehicle type will be 2X, which is inverse of this. So now what do? We basically sum all of these values up, 6, 0.5, 1, 4.5, and all of these, we sum them and we divide each column, by these values, and we get a normalized matrix. So 1 divided by 6 will be 0.17, 2 divided by 6 will be 0.33, and so on. 3 divided by 6 will be 0.5, and so on. So this is the normalized matrix. And now we want to find out the weighting. So what do? We add all of these values together. This is 16, this is 25, and this is 59, right? So what this essentially gives us, this gives us the weighted weights of all of these features. So vehicle type will be given a weightage of 16%, car color will be given a weightage of 25%, and mileage will be given a weightage of 59%. So this is the normalized approach in AHP. Now for each feature we do the same thing for all of the unique values in that feature. So for example, vehicle type will have hatchback, sedan and SUV, and we give priorities of each of them, and then we get the normalized weight matrix, and so on for color and for mileage. Now how do we analyze this? Vehicle type has a weightage of 16%, color has a weightage of 25%, mileage has a weightage of 59%. Okay, now if you just look at this very carefully, all of the colors in the color column, red will have a weightage of 4%, blue will have a weightage of 5%, white will have a weightage of 7%, and so on. So you can get the weightage of each and every item in the complete table, in the complete list of items. So now by using all of these weights, we can calculate the best car for us according to the feature benefits, and the best car is going to be Maruti Ignis, having a vehicle type of hatchback and color as white and mileage as 25. So you can see that this is hatchback, so we get an 8% weightage. Then you have white color, so 7%, and then you have 25 mileage, which is 16%. So 31%. So 31 will be the score of the weights which will be assigned to Maruti Ignis. Now we'll do a cost benefit rate analysis to decide which car is most efficient to buy. This car, Maruti Ignis, was the best car to buy according to the features. Now let's imagine that we have the prices also. So these are the cars, vehicle type, color and mileage. These are the features that we just added. So you can see Maruti Ignis will have 31%, Hyundai i10 will have 36%. So let's say that we want to calculate for Hyundai i10, hatchback, red, and mileage is 20. So hatchback is 8, red is 4 to 12, 12, 8 plus 4, 12, and 20 is 24. So 12 plus 24 is 36. So yes, 36. So all of these values are calculated according to these features. So these are the features. And then you have the on-road price of each of the cars. 6,50,000 and all of these. Right? So this is the total cost. We calculate the total cost, then we get the cost percentage. So 6,50,000 will be what percentage of how much is this? This is more than 10 lakhs. I don't know, 200 lakhs, something like this. 210 lakhs. So what percentage of this? So it is approximately 3%. So we do this for each one of them. So we now have the feature weighting, and we now have the cost weightage. Sorry. So we have two weightages, and now we want to find out which is the best car for us to buy according to these two things. We conclude that by using AHP, we compared various segments of car based on their price and feature benefits, and found the most efficient car in segments in Hyundai i10 hatchback. In hatchback, it is Hyundai i10. So let's look at this. In hatchbacks, we have Hyundai i10. So color is red. So the feature is 36% and the cost is 7 lakhs. Okay. And in sedan, we have Honda Amaze. So in sedan, let's look at sedan. So Honda Amaze, black color, features 24 and 5% and on-road. Okay, so we basically divided each of these according to the vehicle type. Now SUV Toyota Fortuner and Audi Q7 stand at same feature while price is higher for Q7 due to brand value. So Toyota Fortuner and Audi Q7. Audi Q7 is SUV and Toyota Fortuner. Okay. So the price is same, but the cost percentage of Q7 is more because of brand value. Okay. Now let's look at Topsis. Topsis is an abbreviation for Technique for Order of Preference by Similarity to Ideal Solution. So we find the order of preference of all of these features by finding the similarity to the ideal solution. Now, how do we find out the similarity to the ideal solution? We use a geometric distance or Euclidean distance for this. So as you can see, it is based on the concept that the chosen alternative should have the shortest geometrical distance from the positive ideal solution and the longest geometric distance from the negative ideal solution. So we'll be having two ideal solutions, and I'll be showing you what this means. So a method of compensatory aggregation that compares a set of alternatives by identifying weights for each criterion, normalizing scores for each criterion. So we'll have different criterions and we'll be normalizing them accordingly. So we'll look at this by the example. And again, we can see that this means the same thing. We calculate the geometric distance between each alternative and the ideal alternative, which is the best score in each criteria. However, an assumption of Topsis is that the criteria are monotonically increasing or decreasing. So this is very important because all of the criteria in Topsis have some ordinal relationship between them. I'll be emphasizing this. I'll be showing you what this means in the next slide. So let me just show you. If you just look at this looks column, looks feature, we can just look at all of these features, not just looks. Let's look at the price one. So the price has 250, 200, 300, 275, 225. So this is in some particular order. Same goes for storage space. This is in some order, and camera also in some order. Now, if you look at looks here, you have got excellent, average, good, good, below average. We want them to be in some order. So we use a 5-point scale by assigning them some score, and we convert them by doing some label encoding. This is called label encoding. So is a criterion monotonically increasing or decreasing? Normalization is usually required as the parameters of criteria are often of incongruous dimensions in multi-criteria problem. So the normalization was done in AHP, and this will be done in Topsis as well. Topsis provides a more realistic form of modeling than non-compensatory methods, which include or exclude alternative solutions based on hard cutoffs. Okay, so now let us look at an example for Topsis. We have different mobiles and we have the cost of each mobile, the storage space and the camera and the looks. As discussed earlier, we can't keep all of these looks in the form of a text. So we kind of label encode them to make them an ordinal feature. So this will be a categorical feature having an ordinal value. So categorical feature means that that this feature looks is a feature, and it is categorical because it has some fixed finite number of values which it can achieve, and it is also ordinal in nature because all of these values have some particular order. For example, 2 will always, the 2 signifies that the looks of 2 is less than the looks of 3 and the looks of 4 is less than the looks of 5. So there is a particular order here, so that is why it is ordinal. Okay, so now we normalize this, and the normalization is pretty easy. So the normalization is not as sum we were doing in AHP. We were just adding all of these values and then dividing it. It's not like that. We basically take the square of each of these values, we sum it up, and then we take the square root, as you can see. So we do it for this, for this, for this, for this, all of these, and this is what we get. Okay, now after doing this, we divide each of these items by this value. So this is what we get. And finally, this is our normalized matrix. And now we add some kind of weights to each feature. These are the weights where we can basically assign equal weights like 0.25, 0.25, 0.25, 0.25, or we can assign some different weights as per the convenience of the person who is solving the problem. For example, you might think that, okay, let's see that the price would require some more weights than storage space. So you can just assign it as per your own requirements. So you assign some weights and you multiply these items with the weights. So this is the weighted normalized matrix. And now these are the two things that I was talking about in the first slide. Vj plus indicates the ideal best value and Vj minus indicates the ideal worst value. So now let's look at them. Okay, so in the weighted normalized matrix which we just had, we solve for each column Vj plus and Vj minus. Vj plus means ideal best value. So let's look at storage space, for example. Let's look at storage space first. In storage space, what will be the best value for the storage space? It will be the maximum. So 0.1508 is the maximum. What will be the worst value? It will be the minimum, 0.0754. For price, what will be the best value? The best value for price will be the cheapest because you don't want to spend so much money. The best value will be the price. So it will be 0.0886, which is the minimum. So Vj plus will be minimum here. And Vj minus will be the worst, will be the most maximum expensive mobile. So it will be 0.1328. For looks, again, it will be the maximum and minimum. Then for camera also, it will be maximum and minimum. So we get these ideal values. Now we want to find out the geometric distance between the ideal value and actual value. Now how do you do this? We use these two formulas. So let's look at this. We basically take for every mobile, let's say that this is the first mobile, we look at Vj plus and we subtract each value from Vj plus. So 0.1107 minus 0.0886, we take the square of this, plus 0.0754 minus 0.1508, then we take the square of this. Then we look at this and then we take a square of this, then we add all of these and then we take the square root of this, and this will be 0.0863. This is essentially the Euclidean distance. For example, let me elaborate. Let's say that mobile 1 was a coordinate, was a point in some 4D space. x1, x2, x3, x4. And vj plus is also another point having all of these 4 coordinates. What would be the Euclidean distance between these 2 points? x1 minus, let's say y1, y2, y3, y4, x1 minus y1 x square, y1 minus x2 minus y2 square, x3 minus y3 square, x4 minus y4 square, and then whole under root. So this is the Euclidean distance. This means that this ideal solution is ideal best is how much farther away from this actual values. And the same goes for the ideal worst. So we have this matrix that we have the ideal best and the ideal worst values, and we have these distances. Now we'll be using these distances for the performance indicators. So this is the matrix that we have for mobile 1. So mobile 1 is basically this much far away than the ideal best and this much far away than the ideal worst, and so on and so forth. So this is the performance indicator. Performance indicator measures the ratio between the distance of the data item of how far it is from the ideal worst upon the total distance. So we can calculate the performance indicator like this, and the higher the performance indicator, you can just look at this. If the performance indicator is very high, 0.69, then it will be the best mobile. Why am I saying it will be the best mobile? Because if this performance indicator is very high, this means that it is the farthest away from the ideal worst. So it is very far away from the ideal worst, so it will be the best mobile. You could have done it the other way around. You could have taken SI plus and then it would have been other way around. So that's okay, no issues. So the performance indicator 0.69 indicates that mobile 3 will be the best. Then you have this mobile, which will be the second best, then this, which will be third best, and so on. And you can just look at all of these. Sorry, I was wrong. This is the second best. So mobile 3 should be the mobile that you should buy. Okay, so I hope that you get a complete understanding of what AHP and Topsis is and how these are used for solving multi-criteria decision-making problems in business intelligence. Thank you so much.